So the first thing I want to start with today is a reminder of what we did last week. So you can kind of warm up your hands because we're going to do the right hand rule thing again. I'm going to share my screen with you because I want to share a document. And I'm going here. Okay. All right. So can you see that? I know it's sideways. You see that diagram there? Yeah, it's sideways. I can tell Fotini's seeing it. All right. So just a reminder that the way that you put your hand when you're doing the right hand rule is you point at the velocity. Then you have your thumb up. Okay. And your fingers are at a right angle to your index finger. Okay. So in this picture, what it is that you're seeing is you've got magnetic field lines. That would be where your hand is pointing, and they're going to the right on my screen. So that means if a particle enters, if a particle enters that and is going perpendicular, it's going to feel a force down, all right? But if that particle has a negative charge, it would feel a force upward. Well, here in this figure, I'm hoping you can see my mouse moving around. What they're introducing here is a particle that is moving with a velocity that is on the page sort of upward, okay, so perpendicular to this B field. And because of that, it's going to feel a force into the paper. Now, I cannot turn my hand that way. You shouldn't either. You're going to break your wrist. But what they are trying to indicate here in the diagram is just reminding you of two things. One is if you have the configuration with the right hand rule, that the force for a positive proton follows that right hand rule, but a force on a negative particle like an electron would be in the opposite direction. So keeping that in mind, if you look at a charged particle moving into a magnetic field where all those field lines are pointing like drawn on this paper, then you're going to have that particle spiral around those lines. So scrolling down, that means for a proton, it would move, the positive particle is going to move one way and the electron will move the other way. So counterclockwise versus clockwise, depending on how you're looking at things. All right, so that figure and a couple of other figures are shared with you in Google Classroom. I just wanted to highlight that as people were arriving here today. All right. So what I'm going to do at this point is switch over my screen share again. And this is a kind of an experiment. It's going to be an interactive Pear Deck presentation. So what that means for you, if I do this Pear Deck power up, okay, I need to move this out of the way, is you're going to be seeing a code that appears in a minute for you here. Hold on. Oh, whoops. I should have done this before. Teacher login. Yes, I'm logging in. I don't want you to create a Google Slides file. Don't do that. Wait a minute. Nope. Hang on a second. Present this. Here we go. All right. Start the lesson. All right, are you seeing something that says loading? I'm really hoping you are. Yes. Okay, so what you want to do is on a device, hopefully you could do this in another window because you're really just listening to me talking through this presentation. So do you see something that says joinpd.com? Are you seeing that or no?
Yeah, we can see it.
Okay, so you want to join pd.com And the code is JCSZZ, juicy carrots switch zesty zebras. Okay, so, all right, my first student connected, so somebody clearly got in there. So usually it'll tell me, and then once we've got everybody in there, I'm going to start the class. And so you'll be able to see the presentation on your device, and you'll be able to kind of type and do interactive things with it too, okay? All right, I have 9 people connected. Is there still anybody trying to get in there? No? Okay, I'm going to click start class. So again, it's joinpd.com.
I cannot find the website, or something wrong with my website.
Okay, Judy, you could watch. It'll also, I'm going to be recording this, but it just means that you can't interact with it. That's all.
Okay.
All right, so auroras and pulsars. We've been talking about interactions of charged particles with magnetic fields for a while, and this is going to continue on with that. So an aurora is something that you can observe from Earth, or you can observe on other planets actually as well. Auroras are interaction of what is called the solar wind with the Earth's magnetic field. So if you go to Alaska, or if you go to Iceland, or even if you go to places near the South Pole of Earth and you look in the sky, you will see these beautiful displays that often are greens and pinks and reds and sometimes blue in the sky. Have any of you seen an aurora at all anywhere? Just speak up because I can't really see you at this moment.
In movies.
In movies, okay. Anybody in real life? No? Oh my gosh. Okay, we have to get on a trip so you can see these things. This is what they look like. Okay, so this is a time-lapse movie. Are you seeing the animation? Yeah, it's just really incredible. This is really what it looks like. This is not my filming, but I've seen them from Alaska. And it's just really spooky because they do not make a sound. So they're sort of like the Dementors from Harry Potter. So coming off of the sun, which you see in that picture at the bottom there during an eclipse, coming away from the sun are charged particles all the time. They steadily flow off the sun from an area called the corona, ironically, around the sun. If during an eclipse, the moon, which you see there in the picture, passes in front of the sun, blocking it out, and that picture there is showing you the outer atmosphere of the sun. So those are very hot, high energy particles that make their way to the Earth. Okay, so these things are flying through space, not at light speed. They take several days to arrive, but they're moving, you know, at, as I indicated there, 4 times 10 to the 5th meters per second. Okay, so that's pretty fast, but it's not light speed. But there's a lot coming here. Millions of tons of mass per second flowing away from the sun. So not just light, but actual physical particles, ions, electrons, and protons are moving from the sun toward the Earth, and they're going to come here and interact with the Earth. Fortunately, the Earth is protected. Okay, so one of the images that I shared with you, that don't look at it now, but you can go back and look at this. It's kind of similar to this picture that I'm showing you here, is a picture of Earth's magnetic field. Okay, so the Earth has a magnetic field because of the molten center. We think the magnetic field is generated by the fact that you've got an iron core and you've got molten material moving around that. And so here is a drawing showing the radiation belts. So we do have of course, a geographic north and south pole, and we have a magnetic north and south pole. So the Earth is like a huge magnet, and this magnetic pole historically has flipped over. We don't quite understand the mechanism for that. It happens every couple 100,000 years. We're sort of overdue for a magnetic pole flip, but it's a really interesting feature of the Earth's geography, I guess you'd say, geophysics, is that we have this magnetic field and the polarity flips around, okay? So in the top picture, you see that, you know, we have this kind of protective band around us because, as we've already talked about, magnetic field lines do wonky things to moving charged particles. So we, you know, have our vector, we have our velocity, here comes our particle, right? And whether it's negative or whether it's positive, it's going to be directed and driven by the Earth's magnetic field. Yes, Fotini, I see you've raised your hand.
Sorry about the lawnmower in the background. Can you hear me?
I don't even hear it, but go ahead.
Okay. Why does the magnetic field flip over?
If you can figure that out, you probably get a Nobel Prize.
Oh, okay.
So yeah, no, it's one of the most fascinating things, and I will add is one of my like kind of hobby cottage interests. Where now I hear your lawnmower. Where
Yeah.
if you Google the location of magnetic north, it moves around all the time. And by the way, I could go off on a tangent. It's been accelerating recently. So not only is it moving around like that spot at the North Pole, it's been accelerating. And so that has actually been, in terms of its timing, happening as we've had some global warming going on. So makes you wonder, right? If you're redirecting the vector of solar radiation at the Earth, that might affect our climate a lot. So it's very, very interesting. Anyway, but the magnetic field history of Earth is preserved and frozen in places. So if you do ice core drilling, you can look at that. You can look in rocks and things like that to study the history of Earth's magnetic field. I highly recommend taking a geography class in college. You'll enjoy that if you're interested in this stuff. Okay, so anyway, if you think about it, the solar radiation is coming at one side of Earth. Earth, of course, is spinning. We have this magnetic field around us, and those lines are coming in and touching us at the poles. Okay, so what? Well, what happens if those particles are directed, as we've seen, around the magnetic field lines and they're spiraling? Those particles, those electrons and protons, will come in, and I'm not sure if your screen is blocked like mine is, but anyway, the particles will crash with whatever's in front of them. Okay, so here comes an electron, and it's moving at high speed, and it's spiraling in, and it's being, all of the electrons are being kind of channeled, funneled. You can think of the magnetic field lines as funnels to the North and South Pole, and they smash into the atmospheric gases. Well, why is that interesting? Because chemistry. Okay, so you all have taken or are taking chemistry class. What happens when you have collisional excitation? Well, you smash an electron into an atom and you can knock other electrons up. So over here on the right side, I have a collisional excitation picture. Does that look vaguely familiar? Okay, what is that picture about? Somebody explain the chemistry. What's going on in that picture over there on the right? Anybody can explain it. What is collisional excitation? Is this a term from chem you're familiar with?
Yeah. So, when energy of a particular wavelength hits an electron, it jumps up energy levels and it emits colors as it drops back down.
Yes. Okay, great. So you impart energy by this, you know, fast-moving electron or proton for that matter. Something hits the atom, collisionally excites it, if it gets hit with the right wavelength, the right energy, grabs that energy, and then it falls back down because it doesn't want to be in that excited state, right? So it has to jump levels, it can't go between. You remember all of that. Anyway, as it falls back down, it radiates certain wavelengths. All right, so what we see in terms of the auroral lights is this radiation. And where is it coming from? Well, it's most prominent 15 to 30 degrees from the magnetic poles, because if you think about how those lines are coming in, that makes sort of sense. And it's most prominent from certain elevations in the atmosphere based on the atmospheric density and how those electrons and protons are getting through. So they're clearly not making it to the ground most of the time because they're bumping into stuff. So sometimes we see activity as high up as 1,000 kilometers, but most of the time it's 80 to 160 kilometers up. So I like this next slide because it shows you how the auroral colors vary with altitude. Okay, so this graph is showing you height at the top of the page, and then you know, down near the surface of the Earth at the bottom. So you're getting red colors from, try and move this bar out of the way a little bit. Okay, you're getting red colors from the oxygen atoms that are about 200 kilometers up. So if you're seeing red colors in your auroras, they're coming from very high up in the atmosphere. The blue, which I haven't really seen blue. I've seen something I thought was maybe a little blue. That's coming from nitrogen at 100 to 200 kilometers up. And then there are secondary collisions that can give you some yellow and green from the oxygen in there. And most of the time, what you see in the auroras is the greenish color. And then nitrogen that's lower down will give you kind of a pinkish color, right? So if you see auroras of different colors, they're coming from different heights in the atmosphere. So again, generally the green, and some of the color that you see depends on the contrast and how dark it is and all of that too. So keep that in mind. And when you're looking at the ribbons in the sky, look along the edges of the green ribbons to see the differences in the colors. All right, so look how beautiful that is. Isn't that amazing? So you should have, if you're following with the Pear Deck, now I have a lawnmower out there. If you're following with Pear Deck, I think that you have an opportunity now to fill in something. Is there a question for you on your screen or no?
Yeah.
Okay. So I think you write on there, right? I'll give you a minute to respond. And then I think if I click my next screen, it's going to display some of these responses. I'm pretty sure.
Mine isn't letting me type for some reason.
Oops. Okay.
I'll try to reload it. Maybe that'll work.
Yeah, I think it lets me see the responses, but I'm not. Oh, here it is.
What does synchrotron radiation mean?
Ah, okay. I was waiting for somebody to ask that. Okay, so anyone remember what is the synchrotron radiation? Okay, so I'm gonna, hopefully on my screen you'll see this if I go back. I loaded up another figure for you called synchrotronemission.pdf. Okay, are you seeing that on my screen or no? Rather than Pear Deck?
Yeah, I see it.
Okay, all right, so here's a line of magnetic field running straight through the center, and the electron spiraling around that magnetic field, and it's giving off radiation because it's accelerating. Is that what's happening with an aurora? So remember the prior slide that I showed you about how the radiation is getting generated. So in synchrotron radiation, the radiation is coming from the fact that the electron is changing direction. Are we getting auroral radiation because of a change in direction is my question. Let's show the responses. No, it's from collisional excitation. Particles and electrons from the sun flow toward Earth, and low energy electrons crash in atmospheric gases. Electrons collide with one another, causing them to jump energy levels. When the electrons fall back down, they emit, but yes, deleted response. Electron excitement and how it gets hit with energy. Okay, good job. How do I go back? Hide responses. Okay, yeah, so it is not synchrotron radiation. So why are these kind of things related? Well, what I was saying last week is magnetic fields direct charge particles. So here we have an auroral phenomenon, something we see all the time, that's generated by the same kind of driven, directed particles by magnetic fields, but the radiation is coming from a different mechanism. It's coming from collisional excitation and relaxation. Okay, with neutron stars, what we think is happening is the synchrotron phenomenon. So I love this quote over on the left. 5 decades after the discovery of radio pulsars, there is no consensus on what the pulsar radio emission mechanism is. Pretty interesting, right? We still don't know, but what we think is happening is, like I said earlier, this idea of potential synchrotron radiation. Okay, so you've got your neutron star surface, you've got these charges lifting up. This is kind of zoomed into this portion of the neutron star. You've got field lines that are entering in at the poles. You've got particles that are kind of spiraling around there, and it could be synchrotron radiation or it could be some other mechanism of emission, all right? But what we think is happening with pulsars is that the radiation is due to acceleration of electrons. They're changing their direction. They're spiraling around those magnetic field lines. That's not what causes the radiation for auroras. Okay, auroras are radiating because of collisionally excited electrons that then fall back down. Okay, how are these two things connected? Again, both are connected because we have electrons and protons that are directed by magnetic field lines. Okay. All right, so here's another interactive thing. You get to grab these little thumbs that are at the bottom and drag them, and I believe we're gonna see them right in front of us. So a thumbs up to true statements, thumbs down to false statements. So you grab the red thumbs down and put them next to or on top of the statements, or the green thumbs up. So pulsars and auroras both emit electromagnetic radiation by the same physical mechanism. Drag your thumbs. Oh, here we go. Second one is pulsars and auroras both involve charged particles moving in magnetic fields. Pulsars and auroras emit electromagnetic radiation that is primarily at visible wavelengths. All neutron stars are likely to be pulsars. Okay, so the first statement, pulsars and auroras both emit electromagnetic radiation by the same physical mechanism. I see many thumbs down. Somebody's got a thumb up there. What do you think? I like the thumbs down on that one. Okay, we just discussed that. So it's not the same physical mechanism. One is synchrotron radiation potentially, the other one is collisional excitation. It's very unlikely that pulsars would be radiating by collisional excitation. Pulsars and auroras both involve charged particles moving in magnetic fields. Yes, I love the green thumbs. Red thumb, we need you to move away. That second statement is true. Thank you. Pulsars and auroras emit electromagnetic radiation that is primarily at visible wavelengths. Auroras do, but not pulsars. Okay, because pulsars are mostly radio, right? All neutron stars are likely to be pulsars. It seems like we're a little divided there. Let's talk about that one a little bit more. Somebody that said no, do you want to speak up? Why are a lot of people are saying no? Why are you saying no? Anybody? All neutron stars are likely to be pulsars? A lot of people are saying no. Let's look at this again. look at the picture in the bottom, okay? All neutron stars are likely to be pulsars. The idea of the pulsar mechanism is that it's radiating out at its magnetic poles. Suppose all neutron stars were doing this. Why might we not see it? What condition has to be met in order for us to see that lighthouse? Go ahead, Fotini.
Does it have to be like flashing towards us?
You have to be lined up with it, okay? So could all neutron stars be pulsars? Yes, but we just might not be at the right viewing angle. And that's pretty likely that we're not, right? I mean, we have more chance of not being aligned. So it's likely that all neutron stars are doing this. We're just not lined up with them to see it. All right, last pair deck slide, and then we're going to end for today, is pretend your friend was absent from class today. Write what you would say if you had to explain this whole lesson to a friend, and then we'll display the responses. I'm pretty sure on this you can draw. I'm not sure. All right, so let's take our last minute or two here in class. I'm going to show some of these responses. So some of you said, and I'll read them out here, even though we, oh, that one's still being typed. Let me try and move this. Okay. All right, so I'm going to read some of the ones that are completed here. That even though we know that collisional excitation, low energy electrons drop out of the inner radiation zone, are responsible for auroras here on Earth, we do not know if they are directly responsible for pulsars. Yes, and I would add that we're pretty sure that collisional excitation is not the mechanism for radiation of pulsars. We're fairly sure of that, but we know that particles are directed by the magnetic fields of pulsars. Auroras are the interaction of solar winds with the Earth's magnetic field. Yes, that is correct. Auroras are a similar phenomenon to pulsars in some ways. However, they use a different method than pulsars, electron excitation. They can best be seen near the magnetic poles of Earth. Good. In order to see a pulsar, you have to be lined up with it. Yes, that is true. I would explain to them what an aurora is, and then explain why they emit light. Then I would explain how they're similar to pulsars, but also explain why they're different. Collisional radiation versus synchrotron. Good. Learned about how auroras work, collisional excitation, how that relates to how we think pulsars work, synchrotron radiation. Nice. Main topic today was auroras, and something interesting to me is they don't make sounds. Yes. Auroras are cool, silent things in the sky that exist by electrons coming off of them. Yep, love all those. And last but not least, I will tell you that tomorrow we're going to do a cool lab where we're actually going to observe auroras. So I'm excited about that. All right, have a great day, guys. I know you have class in like 4 minutes, so I'll let you go. Bye.
Thank you. Bye.
Thank you.
Thanks, Mr. Gappy.